Look up at the night sky. What do you see? A vast canvas of stars, planets, and galaxies stretching out into the darkness. Now imagine that what you see is only a tiny fraction of what's really out there. A universe hidden from our view, tucked away in dimensions we can barely comprehend. Our senses perceive only a sliver of reality, a three-dimensional world bound by length, width, and height. But what if I told you that our universe might be much more complex, a tapestry woven with additional dimensions beyond our everyday experience? The idea may seem like science fiction, but it's a possibility that has captivated physicists and mathematicians for decades. Our journey begins with a simple question. What are dimensions? Imagine a line. This line represents a single dimension. Now, add another line perpendicular to the first, and you create a plane, a two-dimensional object. Stack multiple planes on top of each other, and you have a cube, a three-dimensional structure. We experience these three spatial dimensions every day. But what if there are more dimensions beyond these three? Dimensions we cannot see or touch, yet they influence the very fabric of our reality. This is where our familiar understanding of the universe begins to unravel, leading us down a rabbit hole of mind-bending theories and tantalizing possibilities. We'll explore the frontiers of theoretical physics, from the elegant equations of string theory to the bizarre world of quantum mechanics. We'll delve into the concepts of parallel universes where countless versions of ourselves might exist, and ponder the implications of a multiverse, a boundless expanse of interconnected realities. So fasten your seatbelts and prepare to journey into the mind-boggling realm of higher dimensions. Our exploration will challenge our perceptions of the cosmos and ignite our imaginations with the infinite possibilities that lie beyond the familiar. To grasp the concept of higher dimensions, we must first establish a clear understanding of what dimensions are. In the simplest terms, a dimension is a direction or an independent coordinate that defines a point's location in space. Imagine an ant crawling along a tightrope. From the ant's perspective, its world consists of a single dimension, a straight line stretching forward and backward. It can move only in those two directions. Now, picture a flatworm living on a piece of paper. This worm experiences two dimensions, length and width. It can move up and down, left and right, exploring a flat plane. Finally, visualize a bird soaring through the air. The bird enjoys the freedom of three dimensions, length, width, and height. It can navigate a vast three-dimensional space, moving in any combination of these directions. We, like the bird, perceive the world in three spatial dimensions. These dimensions form the foundation of our everyday experience, but physicists and mathematicians propose the existence of additional spatial dimensions beyond these three. These higher dimensions are not as easily perceptible as the ones we experience daily. They are thought to be curled up or compactified at incredibly small scales, far smaller than anything we can observe with even our most powerful microscopes. Although we cannot directly perceive these higher dimensions, their effects may be evident in the laws of physics and the behavior of subatomic particles. To delve deeper into these concepts, we will explore two of the most prominent frameworks that suggest the existence of higher dimensions: string theory and quantum mechanics. These theories offer a tantalizing glimpse into a realm where our understanding of reality is challenged, and the possibilities are as vast as the universe itself. Stepping into the realm of higher dimensions requires a shift in perspective. Imagine trying to explain the concept of up to the flatworm living on a piece of paper. The worm, confined to its two-dimensional world, cannot fathom a direction perpendicular to its plane of existence. Similarly, visualizing dimensions beyond our three-dimensional reality can be challenging. One way to conceptualize higher dimensions is through analogies. Imagine a two-dimensional universe existing on a flat sheet of paper. The inhabitants of this universe, unaware of the third dimension, perceive only length and width. Now picture a three-dimensional object, like a sphere, passing through their two-dimensional world. The inhabitants would only see a series of two-dimensional slices of the sphere appearing and disappearing, changing shape as the sphere moves through their plane. This analogy, while imperfect, illustrates how higher dimensions might interact with our own. Just as the sphere exists in a dimension beyond the flatlander's perception, higher dimensions could be all around us, influencing our universe in ways we are only beginning to understand. These higher dimensions might hold the key to solving some of the most perplexing mysteries in physics, such as the behavior of gravity, the nature of dark matter and dark energy, and the unification of all fundamental forces. The idea of higher dimensions is not merely a mathematical trick. It has profound implications for our understanding of the universe and our place within it. It suggests that our reality is far more complex and interconnected than we ever imagined. Section 4, String Theory, Vibrating Strings of Energy. String theory, one of the most ambitious and mind-bending theories in modern physics, proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating strings. These strings are incredibly small, far smaller than anything we can observe with current technology. Imagine a single atom. Now picture something a billion times smaller than that atom. That's the scale of a string. According to string theory, these minuscule strings vibrate at different frequencies, and these vibrations give rise to all the fundamental particles and forces we observe in the universe. Just as different vibrations of a violin string produce different musical notes, different vibrations of these fundamental strings produce different particles and forces. Here's where things get really interesting. String theory requires the existence of extra spatial dimensions for its equations to work. Most versions of string theory require 10 or even 11 dimensions. These extra dimensions, as we discussed earlier, are thought to be compactified, curled up at an incredibly small scale, explaining why we don't experience them directly. Think of a garden hose viewed from a distance. It appears as a one-dimensional line, but upon closer inspection we see that it has a second dimension, curled up in a circle around the hose. Similarly, the extra dimensions proposed by string theory could be curled up at such a small scale that they are hidden from our view. String theory, if proven correct, could revolutionize our understanding of the cosmos. It could provide a unified description of all fundamental forces, including gravity, something that has eluded physicists for centuries. It could also offer insights into the nature of black holes, the Big Bang, and the very fabric of space-time. Section 5, the quantum realm where dimensions blur. While string theory operates in the realm of the very large, quantum mechanics delves into the bizarre world of the very small, the subatomic realm where the laws of classical physics break down. In the quantum world, particles behave like waves, existing in a superposition of states, meaning they can be in multiple places at once. The act of observation collapses this wave function, forcing the particle to choose a definite state. Quantum mechanics also introduces the concept of quantum entanglement, where two particles become linked even across vast distances. When the state of one particle is measured, the state of the other particle instantly changes, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our understanding of causality and locality. So, how does this relate to dimensions? Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that each quantum measurement or interaction causes the universe to split into multiple parallel universes, each representing a different outcome of the measurement. In this view, every possible quantum outcome exists in its own separate reality. Imagine flipping a coin. In our everyday experience, the coin can land on either heads or tails, but in the many worlds interpretation, both outcomes occur. The universe splits into two parallel realities, one where the coin landed on heads and another where it landed on tails. This mind-boggling concept implies that an infinite number of parallel universes might exist, each slightly different from our own, branching off with every quantum event. These parallel universes, if they exist, could reside in higher dimensions, inaccessible to us but influencing our reality in subtle ways. The quantum realm, with its strange and counterintuitive laws, challenges our traditional notions of space, time, and reality itself. It hints at a universe far more complex and interconnected than we ever imagined, a universe where the boundaries of dimensions might blur and the impossible becomes possible.